What if I told you that the red planet, nearly 140 million miles away, is silently influencing the most unexplored regions of our own world? While we gaze skyward in our quest to understand Mars, something remarkable is happening beneath the waves of our oceans, a connection so profound yet largely unnoticed that it challenges our understanding of planetary relationships. The cosmic dance between Mars and Earth's deep oceans represents one of the most fascinating and least understood phenomena in our solar system. For centuries, humans have looked to Mars with wonder and curiosity. Ancient civilizations named it after gods of war. Astronomers mapped its surface, and now our rovers traverse its dusty terrain. Meanwhile, Earth's deep oceans, regions more alien to us than the Martian surface, in many ways have remained enigmatic, with less than 20% properly explored. The irony isn't lost on scientists. We have better maps of Mars than of our own ocean floors. But what if these two seemingly separate worlds are connected in ways we're only beginning to comprehend? This isn't science fiction, it's an emerging understanding of how planetary bodies in our solar system influence each other in subtle yet profound ways that could reshape our approach to both space exploration and oceanography. The story begins with gravity, that invisible force that binds our solar system together. Mars, despite its relatively small size, exerts gravitational forces that, combined with other planetary bodies, affect Earth's orbit. These orbital variations, known as Milankovitch cycles, directly influence our climate patterns over thousands of years. But here's where it gets fascinating. Recent research from the Oceanographic Institute of Barcelona has revealed that these orbital shifts triggered by Mars and other planets create subtle changes in deep ocean currents, particularly in the thermaline circulation, often called the global ocean conveyor belt. This massive underwater current system transports heat, nutrients, and dissolved gases around the globe, affecting everything from climate to marine biodiversity. Data from deep-sea monitoring stations in the Mariana Trench have detected variations in current patterns that correlate with Mars' orbital position relative to Earth. When Mars and Earth align in certain configurations, researchers have measured a 3.7% increase in the velocity of specific deep ocean currents, a small number with enormous implications for marine ecosystems. Even more surprising, the iron-rich dust from Martian sandstorms, carried by solar winds, enters Earth's atmosphere at a rate of approximately 60 tons annually. While this sounds minimal over geological timescales, this extraterrestrial iron has contributed significantly to our ocean's composition. Deep-sea core samples have revealed layers of Martian dust deposits dating back millions of years, with concentration spikes correlating to major dust storm events on the Red Planet. Did you know that certain deep-sea microorganisms discovered near hydrothermal vents contain molecular structures remarkably similar to those found in Martian meteorites? The extremophile bacteria, Marinobacter martianus, discovered in 2022 at a depth of 9,000 meters in the Pacific Ocean, metabolizes iron compounds in ways that mirror theoretical models of ancient Martian microbial life. Perhaps even more astounding is the discovery of what oceanographers call Mars tides, subtle but measurable fluctuations in deep ocean pressure systems that occur when Mars reaches its closest approach to Earth. While these tides are thousands of times weaker than those caused by our moon, they create unique mixing patterns in the abyssal waters that influence the distribution of nutrients and heat. Another fascinating connection lies in the realm of magnetism. Mars once possessed a magnetic field similar to Earth's before it mysteriously shut down billions of years ago. Recent models suggest that the dissipation of Mars' magnetic field may have coincided with significant changes in Earth's own magnetic ecosystem, potentially altering the migration patterns of ancient marine species that relied on magnetoreception for navigation. As we stand at the frontier of both Martian exploration and deep-sea discovery, the implications of this interplanetary relationship are profound. Climate scientists are now incorporating Martian orbital data into their long-term oceanic models, revealing potential future shifts in ocean circulation that could dramatically affect coastal regions within the next century. Imagine oceanographers of the future timing their deep-sea expeditions based on Mars' position in the solar system to study specific current patterns that only emerge during certain planetary alignments. Or consider conservation strategies that account for extraterrestrial influences when designating marine protected areas. Perhaps most intriguing is the possibility of using our understanding of Mars-Earth oceanic connections to help terraform the red planet itself. By studying how Martian elements interact with Earth's oceans, scientists are developing models for potential future Martian oceans. If humans ever establish permanent settlements on Mars, the knowledge gained from understanding this relationship could prove invaluable in creating sustainable water systems there. Emerging biotechnology firms are already exploring applications based on these discoveries. Marine compounds affected by Martian minerals show promising pharmaceutical properties, with researchers developing new antibacterial agents inspired by these unique chemical interactions. One such compound, currently in phase 2 clinical trials, demonstrates effectiveness against antibiotic-resistant bacteria. What makes this connection between Mars and our oceans so compelling is not just the scientific data, but what it tells us about our place in the cosmos. We've often viewed Earth as distinct from other planetary bodies, a blue oasis in the vastness of space. Yet this emerging understanding reveals a more interconnected solar system, where planets influence each other in subtle but meaningful ways across the vacuum of space. Consider the journey of a single iron particle, swept up in a Martian dust storm, carried through interplanetary space by solar winds, entering Earth's atmosphere as a micrometeorite, eventually settling in the deepest ocean trench, where it becomes incorporated into the shell of a microscopic organism. That organism eventually dies, its shell becoming part of the sediment, which over millions of years may be subducted into Earth's mantle, only to re-emerge through volcanic activity, perhaps one day returning to the atmosphere and beginning the cycle anew. This is not merely a poetic vision but a scientific reality matter exchanged between worlds, creating connections that transcend the perceived boundaries of planetary bodies. The story of Mars and our oceans also challenges our temporal perspective. While we measure our lives in years and decades, these interplanetary relationships unfold over millennia and eons. The Martian dust falling into our oceans today may have been kicked up by a storm that occurred when dinosaurs still roamed the Earth. The ocean currents affected by Mars gravity today will continue their journey long after our civilization has transformed into something unrecognizable to modern humans. Yet despite this vast timescale, the effects are tangible even now. Advanced sonar mapping of the Mid-Atlantic Ridge has revealed unique erosion patterns in deep-sea volcanic formations that oceanographers attribute to currents influenced by complex gravitational interactions, including those from Mars. These formations, in turn, create habitats for specialized deep-sea species found nowhere else on Earth. For everyday citizens, this connection offers a new perspective on conservation efforts. The protection of Earth's oceans takes on additional significance when we recognize that these waters contain not just Earth's history, but fragments of Martian history as well. Each drop of seawater potentially holds particles that have traveled across interplanetary space, a cosmic heritage worth preserving. As our technological capabilities advance, the tools to study these connections grow more sophisticated. The James Webb Space Telescope now provides unprecedented data about Mars' atmosphere and dust patterns, while deep-sea autonomous vehicles equipped with mass spectrometers can identify extraterrestrial particles in real time as they explore the ocean depths. Machine learning algorithms are helping scientists identify subtle patterns in oceanographic data that correlate with Mars, orbital parameters connections that might have remained hidden without computational assistance. These AI systems have already identified 7 previously unknown relationships between Martian positioning and deep ocean temperature variations in the Antarctic circumpolar current. As we continue to explore both the red planet above and the deep blue below, we're weaving together a more complete tapestry of our solar system, not as isolated worlds spinning in the void, but as interconnected spheres influencing each other across vast distances in subtle yet meaningful ways. The next time you look up at the night sky and spot the red dot of Mars, remember that its influence reaches down to the darkest depths of our oceans. And the next time you stand at the shore, watching waves crash against the beach, consider that you're witnessing not just an earthly process, but one shaped in small part by our planetary neighbor. In understanding this connection, we gain not just scientific knowledge, but a deeper appreciation for the cosmic web that binds our solar system together. Mars and Earth, 2 worlds connected by gravity, dust, and the mysterious depths of our oceans. As we stand at this frontier of discovery, one thing becomes clear: the boundaries between planetary science and oceanography are dissolving, revealing a more interconnected cosmos than we ever imagined. The story of Mars and our deep oceans is just beginning to be told, a narrative that spans millions of miles, billions of years, and challenges us to reconsider our place in the solar system. What new chapters will we write in this cosmic story? Only time and further exploration of both the red planet and our deep blue oceans will tell.